Hello everyone. In this video, we're going to walk through an example of how to use four-pole parameters to derive an expression for velocity transmissibility of a single-stage mounting system. This is very similar to a problem that's on the homework, problem number 1 for lesson number 10. The main difference between this problem and the homework problem is that here we're being asked to derive an expression for the velocity transmissibility of this system. And so here we can read the prompt. Use four-pole parameters to derive an expression for the velocity transmissibility. In this case, we're describing the transmissibility as the ratio of the vibration velocity into the roof compared to the input into the system, into the equipment mass. We're asked to find that transmissibility for an air conditioning unit on a resilient mount attached to a compliant roof layer with drive point impedance. So here in this example, we're assuming that we were able to measure the drive point impedance of this roof foundation that we're putting the unit on. And we also have to assume that the air conditioning unit and roof move locally as rigid bodies and the mass of the mount can be ignored. But we do want to consider the damping of the mount in this example, which is another difference between this problem and the homework problem. So in these types of four-pole parameters problems, it's always a good idea to begin by drawing kind of a simple system diagram of what's going on in the problem. So we'll note that we have an input force, which I'll draw this arrow, and velocity, F1, V1, F1 and V1. And these are exciting our piece of equipment. And then we must have some connection between the equipment and the mount. And at that connection, we can say that there must be a force and velocity F2 and V2. And then this is going to be the mount. And then we can draw another arrow between the mount and the roof, with the mount sitting on the roof, and we have, that'll be F3 and V3 as given in the problem statement, connecting to our roof. Okay, so we can also, rather than using this terminology that's kind of given in the prompt, we can actually look at the physical quantities associated with these different elements. So next I'll draw a slightly different diagram showing our input force and velocity, F1 and V1. And rather than calling this equipment, our equipment is essentially just a mass in our system. So I'm going to just denote that with a big M. Here, we'll notice our mount. You might be asking, what should we model this as? Well, we can see in the problem statement that it's described as a resilient mount, so that means it has some stiffness associated with it. And it's also asked us to consider the damping of the mount. So we have both the stiffness and a damping quantity associated with this piece of equipment. And essentially what we'll do then is model this mount as a dash pot providing damping and a spring providing stiffness in parallel. So I'll go ahead and draw that now. We'll have our dash pot here and our spring. And to denote the dash pot or the damping provided, I'll just have a big D there for dash pot and a big K here for the spring stiffness. And then this is going to, since this is the representation of our mount, this then connects into our roof. And our roof, at the drive point, we know the impedance, we were able to measure it. So this is just going to then provide, the roof will be our ZF term, our drive point impedance. Okay, now we can go ahead and start to now we can go ahead and start to derive matrix expressions for our system. One thing to note is that we still do have our F2V2 term and our F3V term, F3V3 term here. I just don't have room to draw the arrows. But okay, we can go ahead now and start deriving matrix expressions for these elements. So I'm going to start by deriving an expression for the mass, which I'll indicate in blue here. So essentially we'll develop our matrix expression as follows. We'll have our force and velocity vector, and we'll set that equal to some matrix of 4-pole parameters. We don't need to get super into the details yet, so instead I'm just going to draw this mass matrix as a giant M in our formulation, and then later we'll go in and actually substitute the 4-pole parameters. But to keep things simple now, we'll use these big letter abbreviations. And then that will equal the mass matrix multiplied by the output vector here, which is going to be our F2 V2 term. Okay, that's our mass. Now we can go ahead and develop an expression for the spring and dash pot in parallel, which I'll do in pink here. So for this element, we'll have our input F2 V2 vector. We'll have our element matrix here full of the 4-pole parameters for a spring and dash pot in parallel. To keep that simple, I'm just going to write that as an abbreviated K parallel D for the spring in parallel with the dash pot, and then multiply that by our output vector of F3 V3. Okay, now we can see we have these two relations developed. If we want to examine the relationship between the input velocity at V1, remember our goal ultimately is to get to velocity transmissibility relating velocity at point 1 to velocity at point 3. It would be a good idea to plug this equation that we've developed into our first one, so that we get a term that's we get an equation that's in terms of V1 and V3. So we'll go ahead and do that. We'll start with the input vector at 1. That is set equal to our big mass matrix, and then now we're substituting in this second vector into our relationship here. So we'll have our K parallel D multiplied by F3 V3. Okay. Next, we can now go ahead and actually fill in the values for these matrices. So the 4-pole parameter matrix for the mass term will be given by equation 10.11 in the notes, and the 4-pole parameters for a spring and dash pot in parallel, that will be given by equation 10.23 in the notes. To help keep things moving, I've gone ahead and worked through some of the upcoming matrix math off screen. If you'd like to practice doing the actual steps yourself, I encourage you to pause the video, give things a try yourself before watching the rest of the video. So our next step will be to actually plug in the matrices containing the 4-pole parameters for our mass and our spring and dashpot matrices using equation 10.11 and equation 10.23 in the notes. And that's what I've done here in this next step. Then we'll want to actually multiply these two matrices together. And it's all right if it's been maybe a little bit since you've looked at matrix multiplication or feeling a little bit rusty on the subject. I'll go ahead and show what the fully multiplied matrix looks like here and talk through the steps that we actually took to get each element. So you might recall with matrix multiplication, to get the first element of the resulting matrix, we multiply the first row of the first matrix by the first column of the second matrix. To get the second element of our resulting matrix, we multiply the first row of the first matrix by the second column of the second matrix. To get our third element of the output matrix, we multiply the second row of the first matrix by the first column of the second matrix. And then to get the final element of our resulting multiplied matrix, we multiply the second row of the first matrix by the second column of the second matrix. Then we'll see in the next step that we can simplify the terms in this matrix just a little bit. And then next we'll want to multiply our output vector F3, V3 into this matrix to arrive at these two equations seen here. Since in the original prompt we are interested in the velocity transmissibility V3 over V1, if we look at these two equations, we'll see that the second equation, which contains V1 and V3, that will be the one that we're more interested in. To start to get it to look a little bit more like what we are ultimately interested in, V3 over V1, which I'll just write over here since that's what we're interested in. We'll go ahead and divide this equation by V3. So after doing that, we'll end up with V1 over V3 equals, I'll just use white for this, 1 over C plus K over I omega times F3 over V3 plus V3 over V3, which that will just become 1. Okay, let's also recall that back in the problem statement, it is stated that the drive point impedance of the foundation is known, given as ZF. So we'll write that here, ZF. And let's recall that the drive point impedance is defined as the force divided by the velocity at the location where it was measured, in this case at the foundation, so we've defined that as F3 over V3. Then we can substitute that into our equation where we have F3 over V3. And we can rewrite our equation as V1 over V3 equals 1 over C plus K over I omega times our drive point impedance ZF plus 1. And we've almost arrived at our desired velocity transmissibility quantity V3 over V1. And in order to do that, we're just going to flip our entire equation. Thus arriving at V3 over V1 is equal to 1 over C plus K over I omega times the drive point impedance ZF plus 1, and I'm just going to take the inverse of that. And that'll be our final answer. Understanding that this result might not mean much to you in its current form, I can go ahead and scroll down and plot the velocity transmissibility across frequency for a given system. So in this example, I've substituted some reasonable values representing the equipment being mounted on an existing lightweight roof. The existing condition is the dark blue line. An existing lightweight roof with a mass that is still significantly greater than the mass of the equipment itself. I've indicated the specific operating point or frequency the equipment is operating at. Then I've plotted a comparison with some incremental changes. So, for example, if the impedance of the roof layer was increased by increasing mass and or stiffness of the supporting structure, we see that the velocity transmissibility, or really what that's saying is the ratio between the vibration velocity measured at the roof compared to the vibration velocity measured at the equipment, decreases with an increase in foundation impedance. We also then see with a higher impedance roof that decreasing the impedance of the isolator mount, in this case by selecting a less stiff mount, that can further reduce the transmission of vibration into the structure as well. Really what this illustrates is a fundamental concept of vibration isolation systems, which is that we should try to force a low impedance mount to drive a high impedance foundation to reduce the transmission of energy into the structure. This is something that's expanded upon in Course 3 and is also described in the lecture notes on page 19 of the Lesson 10 lecture notes. With that, I thank you for your attention, and please do keep checking back to the Institute of Noise Control Engineering course's YouTube channel for more sample problem content.